So hello, everyone. Welcome to the GReTA-ExACT working group. It is our great pleasure today to welcome Ambroise Lafont, who is currently a postdoc in the Type Foundry project in Cambridge. And he will tell us about a prototype for an editor with which one can reason about commutative diagrams. And I just wanted to briefly say before Ambroise starts, for the session today, we will live stream the talk part of this working group and a short demonstration of the tool. But then afterwards, for the questions, I would ask everybody who is on YouTube and wants to join us to register for the Zoom meeting. The registration will remain open, and we will then switch off the YouTube live stream to have sort of an informal discussion on this tool. And so without further ado, Ambroise, thanks a lot for being here, and I pass over to you.
Okay, thanks, Nicolas, for the introduction, and thanks for inviting me to this seminar. So what I'm going to present is a diagram editor that I have been implemented in the last few years in order to help me formalizing commutation proofs. So the motivation for this editor is that I find that diagrammatic reasoning is quite useful when I'm proving things category theory, but the theorem provers that I use, like Coq, are text-based. So this is why I thought that there was a need for a tool to bridge the gap. So what I'm going to present is one step toward bridging this gap. So for the purpose of this talk, I will refer to this editor as YAD. It's not a definitive name, but I need a name to refer to it, so I will use it. So the idea is that you can use it first to load an equation from Coq, and it will turn it into a diagram. Then you can work on the editor side, build your commutative diagram, and then it will generate back a proof script, that Coq proof script that you can use. But I will tell more about that later. But the idea is that it will leave you currently it leaves you the gaps, the proof of the subdiagrams to prove manually. So it's available online, so you can try it on this address. So it's run in your browser because it's written in Elm. So it's about 6,000 lines of code currently. So Elm is it's a programming language which compiles to JavaScript. So everything is runs locally. So why I decided to call it yet another diagram editor? It's because there is also a popular diagram editor that already exists, I think, and that many of you already know. It's called Quiver. So it's also a commutative diagram editor online, where you have a lot of display options like colors and so on, and you can export to LaTeX. So YAD is similar to Quiver for the editing part, although it's less sophisticated currently. And it does not have a rigid grid layout. You can, because in Quiver you can only create vertex on a fixed grid, and it's not the case in YAD. But that's a detail. Okay. So yes, so the main purpose of YAD is to generate some proofs. So what I'm going to present now is some of the features that I have implemented that help me formalizing commutation proofs, and then I will do a short demo. I will first explain the format which I use to load equations from Coq into the editor, and I will explain how the support for forward reasoning and backward reasoning. So I will explain what that means. How I understand what I mean by these terms, and then I will end with a demo. So for the parsing equation, so there is a simple format that the editor is able to parse. It's just you write, for example, this is such a diagram. You can represent it with this piece of text. So you have to put explicitly the vertex, and between them you have the label of the edges of the morphisms. So what I do is when I have to prove an equation in Coq, I use some Coq notations to turn the statement that I want to prove into this format, to comply to this format, so that I can load it in the editor. So I will show you in the demo how it works. Now we explain the forward reasoning mode. So the idea for this part is that like a commutative diagram is a proof. So for example, in this example, we have 3 subdiagrams, and what this diagram says somehow is that if each of the subdiagrams 1, 2, 3 commutes, then the outer diagram commutes. So this is what the proof script, the generated proof script will prove. So it will leave you to prove the subdiagram. So the algorithm for the proof generation is quite simple. So here is a sketch. It's first. So the editor first identifies all finds all the subdiagrams on the canvas, and then it starts from one branch, like for example the top right UF, and it repeatedly apply the subdiagram in order to get to the other branch. And okay. Oh, and yes, I should say a bit of word of the current target of YAD. So it generates Cox proof scripts which are to be used with the Unimas mathematical library. So this is a library which started in 2014 based on Voivodsky of repository foundations. It's a very large Coq mathematical library. So last time I looked at it, it was 300,000 lines, and 2/3 are.
Sorry to interrupt you. We have a little issue with your slides. They seem to be somehow lagging a bit. Could you maybe just try to reload that? I mean, it's like the resolution has become really bad. We are trying to figure out what it is.
Can you see now? Or?
Yeah, but I mean, somehow it's a very bad resolution. Do you have any idea what that could be?
Looks good for me. So can you switch again?
For me, it's okay.
Yeah, it looks perfect.
The resolution looks
the Unimas mathematical library, and it looks perfect here.
The resolution looks good, but what I think I and Andrea at least seemed to struggle with was that as you were speaking, when you were switching to the next slide, you seem to be talking about the next slide, but we could still see the old slide.
Okay, sorry.
And then it suddenly after a while we only saw that, but we could see your mouse move and point at things that weren't actually on the screen yet, if you see what I mean. So there seems to be something strange going on there.
Okay, so I should wait a little bit until you get the slide on screen. Okay.
Oh, sorry. Yeah, but let's try again. I mean, maybe it was just glitch. Who knows? Thanks.
Okay.
Sorry.
No worries. So it's a large Coq mathematical library. Also, it has a lot of numbers of lines because the style which is advocated by the maintainers is verbose. So that might explain, but it's also a very extensive library. Anyway, and okay, so there is an issue with it, is that it's inconsistent because the universe level checks are disabled. It's because the way they encode quotients in the library, so they had to disable this check. So that's a bit annoying. So why target this library? It's just that this is a library that I use in my formalization project, but the editor could be. The implementation could be easily adapted to another target, another category theory library, I think. Okay, so just to give an example of how commutation proofs look like in Unimas. So let's say you are working on, you want to prove this, the outer diagram here commutes, and you start from the left bottom branch. And you want to rewrite to apply this subdiagram here.
I don't see the diagram now.
Sorry?
See it. Now it appeared. Okay. Okay.
Oh.
Now I see the diagram. Sorry.
Okay. So
some 10 seconds later. Sorry.
Whoa. Okay.
It's much faster for me, so it depends of connection stuff, I guess.
Could be a problem of connection. Okay.
Oh. Okay. Okay, so let's say you want to rewrite this, to use this subdiagram to rewrite M into SI sigma. So in Unimas, you will first have to, what you do is you have to focus on this morphism first. So On the right-hand side here, these are the coq tactics that you need to write in order to get there. So the first one is use associativity to isolate H0. Then apply cancel precompositions mean that you are going to focus on the right morphisms in the composition. So you need to do it twice to get to M, and then you can apply 5, the subdiagram that you want to apply to rewrite M into Si sigma. So it's a bit verbose. So in coq, you also might expect that you can directly use the rewrite tactic on the lemma. But the thing is, it does not always succeed, and sometimes it works, sometimes it breaks. And when it breaks, it's hard to fix because you do not know exactly where it was writing before. So that's why this verbose style is more robust when you want to use a subdiagram. Okay, so now this is an example of pull script which is generated from, if you draw this diagram on the left. So here on this diagram you have, this is the same as before, you have an outer diagram with 3 subdiagrams. And from the editor, it will you will get a proof script which will prove the commutation of the outer diagram. So this is the goal here, that UF equals Vj. And if you look at the proof script, there are 3 asserts, 3 equations which are asserted and then admitted, and these are the 3 subdiagrams. So, for example, the first one, U equal M P1 is the first subdiagram. P1 F equal P2J is the third subdiagram. Then the last one is the second subdiagram. So you can see how it has generated the proof. It has first applied it started from the top right branch, and then it applied the first subdiagram, and then the second, and then the third subdiagram, and then the second to get to the other branch. And everything between is a boilerplate code to focus on the subterm or the relevant morphism and to apply the equation. And then at the end, you still have to prove manually the subdiagram. Now I'm going to present a bit of support for backward reasoning. So I will explain what I mean by that. So with an example where you suppose you have a natural transformation n between 2 functors j and f, and you want to rewrite using naturality nx composed with ff into jf composed with ny. So the forward reasoning mode, or what I call forward reasoning, is that first you state this equation explicitly and you prove it using naturality. So you state the naturality specialized to this morphism, and then you apply the equation. And when you can do it also backward in the backward mode, it means that so what I mean by that is that you directly apply naturality of n. And then because you take advantage of Coq unification algorithm, so that it will figure out what is the f that it needs to instantiate naturality with, and then the advantage that you do not need to provide explicitly the right-hand side because it will figure it out by itself. So concretely in YAD, what you can do is to do this kind of thing is let's take this example. So on the left-hand side, you have you want to work on the top right branch, and you want to rewrite using naturality these 2 morphisms nx and ff. So what you would do is to create an empty arrow between gx and fy. You select the subdiagram here, and then you ask the editor to generate a Coq script that will in fact just essentially focus on this 2 morphism in the Go. Then you manually apply the lemma in Coq, and then you copy and paste the result in the editor, and it will automatically create replace the empty arrow with the expected hand side. Okay, so now this is time for demo. So I will what I'm going to show is associativity of composite multiplication. So when you have a distributive law between two monad T and S, you can define the composite monad R, which is TS, and you can define new prime multiplication candidate for this monad, which is not yet a monad, but you have to show that it's a monad, you have to prove that this mu prime satisfies three equations, and one of them is associativity, which is here below. So what I'm going to show now is I'm going to show this using YAD. So let me first share my full screen, because I will need to show multiple windows at the same time. Yes, desktop. Okay. Okay, so I hope you can see my screen. So this is the files which I start from. So in the header, I load the Unimas library. There is already definitions of monad here, and here it's my special tactic file. I call tactics. So there are some useful tactics and also some notations. To comply to the graph editor. So here are more notations for monads. And now, in my context, I introduce a category, two monads on this category, and a natural transformation between them. And this is a bit of a notation again for the distributive, for the natural transformation. And the first thing I have to do is to add to the context all the laws that distributive law must satisfy. So I have already drawn them in my editor. So they are here. So there are two laws for multiplication. So this is the first one, the second one, and two laws for unit. So I can turn this. I will just generate a code script and steal the statement of commutativity to put it in coq. So let's do that. So you can see there are four goal statements that has been generated, and each of them correspond to one of the diagrams. So let's start with the first one is a unit law. So let's call it unit 1, and I can just copy and paste like that. The second one is also a unit law. I can just copy and paste. Then I have the multiplication law. Sorry. Yes, and the other multiplication law, which is here. No, I didn't copy it. Yes, same. Okay, so I have all the laws which are now stated in my context, and I need to define mu prime. So the mu prime is multiplication for the composite monad. So it will be given an object of the category. It will go from TS of X, TS of TS of X into TS of X, and it's just defined by first. I first apply the distributive law, and yes, it should be this one. and then I apply the multiplication of both monads. So let's start with the monad T, the multiplication for T. And then the multiplication for S. Yes, okay. And what we want to prove now is that mu prime is associative. So this is exactly the commutative diagram that I have shown on the slide. And if you want to write it here, it will be T of S of mu prime of X composed with mu prime. Oops, sorry, it's a bit.
Maybe you should do that using the diagram editor, right?
Yes, I could do that, but I haven't written it explicitly. So yeah, okay, I can do that. Yes, anyway, we have. But I mean, it's a very. It's just I can write it manually because it's just. It's very quick, just this one. So I'll just do it equationally and. But indeed, I could have done this way. And then this one again. Okay, so the first thing I want to do is to unfold this mu. And then I normalize the goal. So what normalize do is it's just, I don't know, maybe I should increase the scale, the font here, the font scale. If you look at this point here, you have functors applied to composition of morphism, and you have parentheses that are explicit here. So what I do is I distribute. I use the fact that functors preserve composition of morphism, and I rewrite. I use a canonical associativity order for the morphism. And now I get a goal here that I can. Yes, so I get the normalized goal, and now I need one more step to load it into the graph editor. It's to make the vertex explicit. So using this format that I have presented you earlier. So this is okay. Maybe yes. Okay. So there is a little. I need to simplify first because otherwise it's a bit ugly. Okay. Okay, so I have entered the equation and it has load the equation as a diagram. So you can see that the format here, this is the first vertex, which I can find here. Then you have the name of the first morphism, which I can find here, and so on. And the other side of the equation, it's the same. Okay, so now what do we want to do? We want to so the game is to use associativity of both monads, T and S. So for example, we need to bring this mu close to this mu T, and this mu S close to this mu S. So let's start, for example, for this mu S, we want to move it to the right, and for this purpose, we can use this distributive law. So to apply it, I will do it in the backward reasoning mode. So I say to the diagram editor that I want to replace this part. Now it will generate some code that will focus on this part. And I'm here. Yes, okay. So now I'm here, and you can see that indeed I am. This is the two morphisms that I want to work on. Duplicate goal is just a tactic that will allow me to copy and pass later the full subdiagram so that I can load it into the editor. Okay, so what I want to do is to apply this multiplication law for the distributive law. But you can see that it's everything here is under a T. So I need to somehow to get rid of this functor T before applying this. So this is what I'm going first to do. So I have this this tactic functor console that allows me to remove the T, and then I can apply the equation. I think it's mu. It's the second one. Yes. Okay. Okay. And then I normalize again, because you can see there is here a composition of morphism, so it's quite inconvenient. So yes. So I just distribute the functor over the composition of morphism, and that's it. And now I can now I have the now I can get back what I have just proven and put it into a format that the editor can read. And I copy it, the goal, and I put it here. And you can see it has a field the empty arrow accordingly. Okay, so that's it. So let's move. So now what remains? What we have in the goal here is correspond to this subdiagram on the right. So I will remove this part here because we don't want to. We want to exclude this part from what we need to do, from what remains. Okay, and now, sorry, up. Okay, so now we need to switch position between mu s and ut. This is just naturality. So I have a tool that can in my editor there is in YAD there is a tool that allows you to build commutative squares based on. So it tries to guess the labels based on naturality. So here, for example, it gets the labels correctly, I think. So that's nice. Now here I can close this subdiagram by using associativity for the monad mu. Okay. So now I'm doing into forward reasoning. So I'm going to fill the diagram and then generate code script at the end. So okay, so that's for mu. Now we need to bring this this mu t. We need to bring it closer to the other one. So again, we are going to move to swap delta and mu t here by naturality. So it's going to be a bit messy. Up here again, we swap by naturality, and finally, sorry, up. We can use here the associativity of mu t. Up. So here I need to. So the label guess is a bit. I need to fix the label guessing, but otherwise it's fine, I think. And okay, so we are in this situation now. We can close here the subdiagram by naturality, I think, because this is just yeah. So we have the S of mu S, and here again we have a naturality, but we have a naturality of delta, I think. So it should be d delta. Okay, so we have filled our diagram. There is one part which remains here that I will leave for later. So I can already generate a code script that will addresses all the subdiagram here. up. So I copy and paste the code. So yes, it has generated one admit for each subdiagram. And let's just check that if they are admitted, the coq accepts the proof. If everything is admitted. Okay, so I think I copied it twice. That's the reason why. Yes, okay. Let's remove this up. So we have a bunch of admits that we need to fill manually. So let's start from the top one. This one is naturality of delta, but it's under T. So I need to remove the T. Yeah, so I use my tactic functor console T, and then naturality. The next one is a complicated one, so I'll leave it. I mean, this one I think is this one, so I leave it for later. So here again we have a naturality of mu t. So here it's not naturality, it's the associativity law for mu s. So, but it's under T, so I need first to remove this, and then I can apply the third monad law. This is how it is called in Unimas. So if you look at it, it's really the associativity for the associativity law. Okay, here it's again the associativity law, but for the monad T. And I think what remains must be naturality conditions. Yes, this is naturality. Naturality again. And here must be naturality. So what remains is this big diagram here that I'm going to. So if you look at it, everything is is applied to T at the top level. So what I can first do is remove this T and work on the simplified diagram. So here it is. So I will work on it on a separate session of my graph editor. So I will put it into a format that the editor can read. Okay, so here we are. This is the equation that we must prove. We can see that here we can close by naturality. And what remains, what remains here is actually exactly this diagram. Yeah, so it's the other multiplication law for the distributive law. Okay, so from this I can simply generate the Coq script with two admits. There is two admits, one for each subdiagram. Sorry about that. I don't know where to put it. Okay, anyway, I copy and paste. So I need to remove this. Up. Okay, so this one is a multiplication law of the distributive law. Is one of the two, and the other one is the naturality. Is just naturality. And my proof is complete. So if I go until the end, okay. So yes, so that was basically it. And yeah, thank you for watching, and that's all I wanted to show you. Yeah, in this demo.
Thank you very much, Ambroise. And as mentioned before, we will now close the live stream, but everybody who wishes to discuss with us should just join us on the live stream. It's just so we will open the floor then to internal discussion. But if you are still on YouTube, please do come join